Pluto is a distant and mysterious celestial body. Once, it belonged to our solar system's global family, but recent alarming statements from well-known astronomers such as Neil deGrasse Tyson and Michio Kaku have pushed Pluto back into the public eye. They have developed a shocking discovery. Pluto might be on a possible collision course with Neptune. However, how could such an incident occur, and what would happen if it did? Is this a rare anomaly of the universe? Or is there more to this coming cosmic event? Join us as we investigate the possibilities of Pluto becoming involved in a Neptune collision. Pluto was once classified as a planet, but it was later renamed a dwarf planet due to its unusual orbit, which keeps scientists' attention. According to recent research by eminent scientists, Pluto's course is dangerously close to Neptune's orbit. Famous astrophysicists like Neil deGrasse Tyson and Michio Kaku have raised concerns about the possibility of a disastrous event, a scenario between these two planets that might pose a serious threat to Earth. But how could such an occurrence happen? Pluto's journey around the Sun is extremely unusual, requiring a remarkable 248 years to complete a single orbit. Since its discovery in 1930, Pluto has completed only one full orbit, adding to its mystique. Not only is Pluto's orbit slow, but it is also extremely elliptical, vastly different from the more circular orbits of the larger planets. To make things more complex, Pluto's orbit is tilted at an angle of 17 degrees with respect to the solar system's plane. This extreme inclination makes Pluto's movement one of the most intriguing in our solar system. One of Pluto's key orbital features is its interaction with Neptune. For approximately 20 years during each of Pluto's orbits, it is actually closer to the Sun than Neptune. This seemingly defies our expectations about planetary positions and naturally raises the question, why hasn't Pluto collided with Neptune? The answer lies in gravitational influences from other celestial objects, particularly the massive planets. When Pluto's orbit was first studied after its discovery, astronomers were baffled by its unusual path. Unlike other planets whose orbits are more aligned with the ecliptic plane, Pluto's orbit stands out due to its elliptical shape and steep tilt. The realization that Pluto's orbit crosses Neptune's was a major scientific focus. Despite these irregularities, Pluto's orbit has remained stable, a phenomenon explained by space mechanics. The three-body problem plays a key role in understanding how Pluto and Neptune interact, along with the Sun's gravitational influence. Predicting the motion of three celestial objects that influence each other gravitationally is a complex challenge, involving concepts such as libration and wobbling. Libration ensures that when Pluto enters the region of Neptune's orbit, it remains at least 90 degrees away from Neptune, preventing collisions. Another stabilizing factor is Pluto's vertical movement in its orbit. When Pluto approaches Neptune or another large planet, its inclination lifts it above or below their orbital plane, providing additional security against potential collisions. Another important phenomenon is known as VZK wobbling, named after researchers who studied space object interactions. This wobbling effect, caused by gravitational forces, helps maintain Pluto's stable yet seemingly chaotic path. Even though Pluto's orbit appears erratic, this mechanism contributes to its long-term stability over extended timescales. The three-body problem is crucial for understanding how gravitational influences shape orbits. Studying multiple celestial objects together improves our comprehension of Pluto's movement, the solar system's dynamics, and even distant stars. By the late 1980s, mathematical simulations demonstrated that despite Pluto's stabilizing factors, its orbit remains inherently chaotic. Small changes in initial conditions can lead to significant long-term differences. However, despite this chaos, Pluto's orbit has remained stable for millions of years, avoiding major disturbances. Recent computer models have provided new insights into how the gravitational pull of giant planets like Jupiter and Saturn affects Pluto. These models suggest that Pluto and Neptune have a unique orbital relationship. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps maintain Pluto's stability. Beyond Neptune, other planetary forces contribute to Pluto's stability. Jupiter's gravity plays a significant role, as does Saturn's. Simulations show that Jupiter's gravitational pull alone is powerful enough to keep Pluto's orbit stable for billions of years. Together, Neptune, Saturn, and Jupiter collaborate to maintain Pluto's safe course, preventing major collisions. These gravitational forces are essential in maintaining order in the solar system. Without them, the system would be much more chaotic, with dwarf planets like Pluto possibly colliding with other planets or being ejected from their orbits. Understanding Pluto's orbit provides valuable insights into the solar system's complex nature. Pluto's case serves as an excellent illustration of how even seemingly unstable orbits can achieve long-term stability through gravitational interactions. This highlights the importance of continued observation and research to better understand our place in the universe. Pluto's study also reveals the unpredictable nature of celestial mechanics. The concept of orbital chaos, where even a small change in a celestial body's position or speed can dramatically affect its long-term path, is clearly visible in Pluto's case. Over time, astronomers have used computational simulations to study Pluto's motion. These models use complex mathematics to simulate how Pluto interacts gravitationally with other celestial bodies. By making small adjustments to variables, astronomers can observe how minor changes impact Pluto's long-term orbit. In the late 1980s, simulations revealed an intriguing aspect of Pluto's orbit. While it remains stable due to factors like libration and gravitational resonance, it is still subject to chaotic variations. Even small shifts in Pluto's initial position or velocity can lead to significant long-term changes in its orbit. Despite this apparent chaos, Pluto's orbit remains relatively stable over billions of years. This paradox, chaotic yet stable, demonstrates the fundamental order underlying celestial mechanics. Predicting the long-term behavior of chaotic orbits, such as Pluto's, remains a challenge, but ongoing research continues to refine our understanding of how the solar system maintains its delicate balance. Simulations, invaluable instruments for comprehending and predicting how the heavens will move bodies, are riddled with uncertainties. They also draw attention to the problems with our predictive models, as any minor error in the initial circumstances can lead to dramatically different results, nearly making accurate predictions impossible. Pluto's chaotic orbit serves as an illustration of the constantly changing and dynamic universe we live in. Despite significant progress in space research and comprehension, Pluto's orbit reminds us how much remains unknown, particularly about gravitational interactions with giant planets. Pluto's movements provide significant perspectives on the larger dynamics of the solar system. Each planet's location can have profound effects on stability and the trajectories of other bodies within the system. This is why astronomers express concerns regarding the possibility of Pluto colliding with Neptune. After all these years, Neil deGrasse Tyson, a well-known physicist and a significant figure in encouraging interest in cosmology, offers an insightful perspective. Renowned for advocating Pluto's reclassification as a dwarf planet, Tyson views this change as an improvement in our understanding of the solar system rather than a downgrade. His approach to celestial mechanics is rooted in constant learning, and Pluto's erratic orbit indicates that there is still much more to discover in space. The attraction to the unknown, including the possibility of disastrous events between Pluto and Neptune, captivates researchers and the general public. Tyson's predictions about Pluto's future take into account its extremely erratic orbit, recognizing that anything from a close pass to a catastrophic collision remains within the realm of possibility. Another well-known physicist, Michio Kaku, joins the chorus of experts voicing concerns regarding Pluto's long-term future. Kaku, famous for his theoretical physics research, delves into the mathematical foundations of planetary interactions. His theories suggest that, although Pluto's orbit appears stable today, the future remains uncertain. Even small gravitational fluctuations between Pluto, Neptune, and other planets could eventually lead to catastrophic consequences. Despite current models suggesting that a collision between Pluto and Neptune is inconceivable, the unpredictability of celestial dynamics means this possibility can never be entirely dismissed. Gravitational interactions continually shape the paths of celestial bodies, including Pluto's. Over vast timescales, Even minor changes in gravitational forces can accumulate, potentially resulting in significant orbital shifts. This uncertainty reminds us that space exploration is an ongoing endeavor. The more we learn about the cosmos, the more we realize how much remains unexplored. Pluto's path is also influenced by broader cosmic events. As the Sun transitions from a white star to a red giant and eventually a white dwarf, the entire solar landscape will change, potentially impacting Pluto's orbit. While the probability of a Pluto-Neptune collision remains low, the inherent uncertainty in predicting celestial dynamics means nothing can be ruled out entirely. Orbital mechanics are complex, and even small shifts can lead to dramatic consequences over billions of years. This ambiguity in Pluto's fate is a testament to the complexity of the solar system and the dynamic nature of the universe. Pluto's continued study is essential for understanding planetary orbits, gravitational interactions, and fundamental cosmic laws. Ongoing observations and new data from Neptune may either challenge or confirm our existing theories. While the idea of a Pluto-Neptune collision may seem remote, it serves as a reminder of the mysteries that remain in space. Our ability to simulate and predict cosmic phenomena has improved, but celestial events, such as a close call between Neptune and Pluto, still highlight the complexity and unpredictability of our solar system. The dynamic nature of Pluto's orbit inspires us to push beyond what we already know, urging us to embrace the mysteries of space. Scientific inquiry compels us to adopt new perspectives and remain open to surprises. As researchers continue investigating the cosmos, they uncover new layers of complexity, reinforcing the idea that we have only just begun to grasp the universe's grand design. Whether Pluto remains in a stable orbit or encounters a cosmic collision, only time and future discoveries will provide definitive answers. As our comprehension of space advances, Pluto's orbit serves as a symbol of the ever-evolving mysteries that challenge and excite scientists. Even though a collision between Pluto and Neptune is unlikely in the near future, the potential for such events underscores how much remains to be learned about the vastness of space. These celestial dynamics invite us to continue questioning how fundamental forces shape the universe, contributing to the ever-expanding field of astronomy. With continuous advancements in space exploration, telescopes, missions, and sophisticated simulations, researchers can study celestial objects with unprecedented precision. These innovations provide fresh insights into planetary gravitational interactions and long-term stability. One of the most exciting advancements in studying Pluto's orbit comes from new observational technologies and space missions. Probes like New Horizons have provided critical information about Pluto and other Kuiper Belt objects, offering deeper insights into the characteristics of these distant worlds. Each new discovery brings us closer to understanding the mechanisms governing planetary motion. Despite Pluto's reclassification as a dwarf planet, it remains an object of fascination and investigation. The scientific community acknowledges its crucial role in broadening our understanding of the solar system's complexities. The debate surrounding Pluto's status has sparked discussions about the definition of a planet and the evolving nature of scientific classification. Pluto's trajectory reminds us that scientific knowledge is fluid, with new hypotheses and data continuously shaping our understanding of the cosmos. While the possibility of a future Pluto-Neptune collision cannot be entirely dismissed, it ultimately reflects the broader theme of unpredictability in space. Astrophysics is driven by the pursuit of knowledge, with scientists striving to understand the fundamental forces governing the universe. The study of Pluto and Neptune extends beyond their individual dynamics, offering valuable insights into gravitational interactions and planetary motion. The lessons learned from these studies have implications not just for our solar system but for planetary systems across the galaxy. Collaboration among scientists is crucial in unraveling Pluto's mysteries. Astronomers, astrophysicists, mathematicians, and physicists contribute their expertise to analyzing Pluto's movements, leading to more precise planetary models. This collaborative effort enhances our understanding of the delicate balance maintaining harmony within the solar system. While a Pluto-Neptune collision seems highly improbable, it serves as a stark reminder of the challenges we face in predicting the behavior of distant celestial objects. Even the most stable systems can be affected by sudden and significant shifts, emphasizing the chaotic nature of the universe. As we continue monitoring Pluto and other distant objects, it is vital to remain open to unexpected findings and refine our models with new data. The history of Pluto's orbit reminds us of the curiosity and wonder that drive space exploration. Even as we uncover more about our solar system's planets and moons, the mysteries of space remain vast. The potential for future encounters between Pluto and Neptune, while unlikely, fuels our pursuit of knowledge and deepens our appreciation for the universe's complexity. Pluto's movements, though seemingly insignificant, represent a microcosm of larger gravitational forces at play. The dance between Pluto, Neptune, and other celestial bodies illustrates the intricate interconnectedness of orbital mechanics. Space is in constant motion, and even the smallest objects can exert significant influence on larger systems. The story of Pluto's orbit is not just about two distant worlds but about the greater quest for understanding and discovery within astrophysics. No matter how much we learn, there will always be more to uncover. As technology advances, we will continue revealing space's hidden mysteries, one discovery at a time. While a collision between Pluto and Neptune is unlikely, their gravitational interactions serve as a powerful reminder of the vast unknowns still awaiting exploration. Pluto's future orbit remains uncertain, and only time will tell how these cosmic forces unfold. However, one thing remains certain: the more we study Pluto, Neptune, and the universe, the more we realize how much remains to be discovered. As we continue investigating Pluto's orbital changes, the effects of gravity on distant worlds, and the intricacies of celestial mechanics, we gain a deeper appreciation for the universe's vastness and complexity. Pluto's story is far from over, and with each new discovery, we move one step closer to understanding its role in the grand cosmic narrative.